Okay, so let's go back to what we were doing before the, so from before the test. What? Me? Oh yeah, questions. Okay.
Is that where it should be pointing? Like at normal force? Or does
Uh,
it really matter where it's pointing?
we cannot really do friction problems yet. Did I assign that number 2? I should have skipped that. So let's just wait on friction, and it'll make more sense when I talk about it. So if I've assigned any problems that have friction in them yet, let's wait on that. Okay. We'll get to that on Tuesday. Any other questions? Homework questions? Okay. So from before exam 2, here's what we're working on. So we're working on kinetics. And all of the forces that we deal with can be broken up into 2 things. So the force types. The first type is the weight. And the weight is easy. It's always just pointing straight down. So that's easy to put in there. It doesn't matter what the object's doing. The weight is straight down. And then the only other type of force is contact forces. And contact forces we can break up into a few types. So first is pushing force. And if you have a pushing force, it's always perpendicular to the surface. Toward the chosen body. And second is a pulling force. A pulling force is one where you could always imagine that it's being applied by a cable. And I'm going to treat it like, so in problems where things are pulling on each other, I'm always going to treat it like there's a cable in there. And cable forces are always parallel to the cable. Away from the chosen body. And then there's one other type of force, that's friction. We haven't gotten to that yet. So we're still talking about pulling. And what I want you to, yes. Yeah. Okay. Yeah. It's a little bit of a weird pulling force because it applies a pulling force to each individual infinitesimal chunk, So, um, so in some ways it acts different than a rope is pulling on a single part of an object. But yes, you would treat it exactly the same way. And you could treat it like as long as you're not worried about the deformations it's causing or whatever, you could treat it as a rope tied to the center of the earth, pulling on the outer part of the earth that you're looking at. Sure, what do you want me to draw a picture of? Oh, of that. I thought it was going to be like joy of painting. Okay, so you can think of gravity like that. He's sort of a fish man. It's Poseidon, yeah, the god of earth, the god of water. I mean, yeah. Okay, okay. So that's how you can think of gravity. Yeah. Well, now I don't want to erase that, but I'm going to. No, I'm not going to fill it. Okay, so we haven't talked about friction yet. We're talking about pulling forces. Um, and I was going to say really the way to think about this stuff is you really want to think of, when you look at a problem, you really want to think of the rules. You could even have the rules for all this stuff like sitting in front of you as you do these problems when you start. Eventually, they'll become sort of second nature, but the idea is, you read a problem and you say, okay, I need to draw a free body diagram. So you look at the rules for the free body diagram. You draw an outline of the thing. You draw a downward force representing the weight, and you go around the boundary looking for forces. You find the first place that the surroundings are contacting the body, and you say, is this a pushing or pulling force? If it's a pushing force, you draw an arrow, a vector that's perpendicular to the surface toward the chosen body. Give it a label, a variable name or whatever, or a number. Go to the next thing. Maybe that's a pulling force. So you draw an arrow parallel to the table away from the chosen body. And that's just the way to do it. It's just a bunch of rules. Like all of your, as a human, you have all these like creative abilities, but I don't want you to use any of those. I just want you to be like a human lookup table while you're doing this stuff. Okay. And you need to ingrain this stuff in your head. Okay. It's a lot of rules, but the only way to approach it is to just think systematically through the rules. Okay. Yeah. That's a pulling force. Yeah. That is the weight. But Ben was asking if um, so you can think of the weight as pulling towards the center. So how is that different than yeah, you can exactly think of that as, you can think of the weight as a rope pulling you towards the center. Yep. But it's a weird rope that never changes the amount of force it applies. Yep. Yeah, sort of inside. As you know, the whole earth is filled with water. It's a sphere full of water. That's why the electric company tells you not to dig too deep, because it'll spring a leak. I shouldn't have to tell you this kind of basic science stuff. No. Yeah, this is all water. Yeah, you can find it on the internet. It's like a big fish tank. Yeah, exactly. That's what I said. Okay, so now we're going to talk about pulleys. And the pulleys that we're going to consider, we're going to always assume that they're frictionless. And massless. Usually you can get pretty good results making those assumptions, because usually the other forces you're dealing with are quite a bit bigger than those. And so the way we're going to use pulleys is if a cable makes contact, and when I say if a cable, and when I say a cable, I also, there's an assumption we're always making about these cables too. We're assuming that these are weightless. Well, let me change that to massless. You can say weightless and massless. Again, that's usually a pretty good assumption, but sometimes in complicated calculations, you have to include the mass. But if a cable makes contact with nothing but pulleys between its ends, then the cable has the same tension everywhere along its length. So the magnitude of that force that we call capital T, it has the same tension T all along its length. And so, in other words, all a pulley does is change the direction of force that cables apply to objects. So a pulley only changes the direction of force the cable applies. I'll just leave it like that. Okay, and maybe some of you have heard or seen examples of what they call pulley advantage, where you hear or you've seen how pulleys are used with so that you can lift, say, 500 pounds of weight by applying 50 pounds of force. And that can be done, but it's not really, it's not the pulley itself that does that. It's sort of a specific way to rig pulleys up that allows the ceiling and whatever the pulleys are attached to take some of that force. And so I'll talk about that later. But I just want to point out that pulley advantage is not sort of an intrinsic part of what a pulley does. All a pulley does is change the direction of the force. Okay? So, let me do an example. Let's say that there's a pulley attached to the ceiling. And let's say this object has a mass of 10 kilograms. And on the other end, you're applying a force to it. And you want to see how much force you have to apply. So what force T is required first to keep the mass at rest, and second, to make the mass accelerate upwards at, let's say, 2 meters per second squared. Okay, well, the rule about pulleys says this force T, that's the tension in the cable, and since all this cable does is go through pulleys, it doesn't touch anything else, the tension T here is the same as the tension T here and here and here, and right where it connects with that box. So we can skip the whole thing with the pulley and just draw a free body diagram of the mass. So there's the outline. There's a weight force of 10 kilograms times 9.81. So that's 98.1 newtons down. And then what's the direction of the pulling force from the rope? Yep, it's parallel to the cable, away from the body, so up. And I'll call that T because it has to have the same magnitude as the T on the other end of the rope. And now we can go to Newton's second law. I'm going to use our usual coordinate system. We haven't been using anything besides this for quite a while. Okay, so the 98.1 is in the negative y direction. So as a vector, that's 0, negative 98.1. The t is in the positive y direction, so that's 0, positive t. And that all together is the net force. Those are all the individual forces. And those are equal to the mass, 10 kilograms, times the acceleration. This is part A. So in part A, what's the acceleration of that box? 0, because it's at rest. The x equation doesn't help, but the y equation says negative 98.1 plus t is equal to 0. So solve that and you get that t is equal to 98.1 newtons. So to hold the box at rest, you have to pull down on the end of the rope with a force of 98.1 newtons. Okay, so any questions about that? So now what if you want to make the box accelerate up at 2 meters per second squared? So we'll start again with a free body diagram. There's a weight force of 10 times 9.81, so that's still 98.1. Whether the box is moving or at rest or accelerating or not, that doesn't change how hard gravity pulls on something or where it pulls. And then the force applied by the cable is parallel to the cable, away from the chosen body. So just like before, it's like this. Is there anywhere else the surroundings are touching the boundary? No. So that's a free body diagram. And notice it doesn't look any different than the free body diagram did in part A. But that's because the only thing changing in this problem is that the box is accelerating. And the acceleration only comes into the problem on the right side of Newton's second law. The free body diagram just gives you all the stuff that you're going to put in the left side of Newton's second law. So it's no different, but the value is going to come out different. Now Newton's second law, since the free body diagram looks exactly the same, the left side of Newton's second law looks exactly the same. You have 0, negative 98.1. Plus 0t is equal to the mass of 10 times, now we're saying that the box is accelerating up with 2 meters per second squared. Up is the positive y direction, so the acceleration is going to be 0, 2. Again, the x equation doesn't give us anything, but the y equation says negative 98.1 plus t is equal to 10 times 2, so 20. And so t is equal to 118.1 newtons. So if you just want to hold the box in place, you have to pull down on the rope at 98.1 newtons. If you want to make the box accelerate up at 2 meters per second squared, you have to pull it at 118.1 newtons. So you have to pull down on the end of the rope at 118.1 newtons. Okay, so what force do you have to apply to the end of the rope if you want to just keep the object moving up at a steady, constant velocity? Say 50 miles per hour. Okay, no, say 5 miles per hour. No, the idea is it doesn't matter what the velocity is. Velocity doesn't show up in Newton's second law. In real life, I mean, there'd be a lot of friction if you were trying to pull this up at 50 miles per hour or whatever. But what Newton's second law says is no matter what the velocity is, all we care about is the acceleration. So this is the acceleration if it's moving up at 50 miles per hour. That's the acceleration if it's moving down at 5 miles per hour or anything, okay? All that matters for Newton's second law for calculating these forces is the acceleration, okay? Any questions about that? That's sort of a weird, hard thing to wrap your head around, I think. But every problem that we're doing for now, if we assume there's zero acceleration, we're getting the answer that would be true if you're making the thing move at a constant velocity of 50 miles per hour. It would be true if you're making the thing move at a constant velocity the other way of 2 miles per hour, because all that we care about is the acceleration. Okay. Often with pulleys, we're going to have, so we'll have objects at each end of the rope, at each end of the cable. And we're going to have to use Newton's second law for each of those objects, one at a time. Okay. And when that is the case, so say you have 2 boxes with a rope in between, and you're pulling on one of the boxes. There is always a relationship between the motion of the 2 objects. So let's say, let me give an example. Let's say that you have an incline that way and an incline that way. And you have an object here and an object here. And a cable going over a pulley between them. In those problems, we'll always have to use the relationship between the 2 objects' motion. So between the motions of the objects. Okay, so what I mean by that is, imagine that you move this box an inch up the ramp. Where is this box going to go? It's going to go an inch down its ramp, right? And not every problem is set up with ramps like this, but there's always going to be some kind of relationship between the motion of those two objects. Or what if you move this one an inch this way? That one's going to go an inch up the ramp. Okay. And the same way it works with, moving it an inch, that's the same relationship that you have between accelerations. So if this accelerates 10 meters per second squared that way, this one accelerates 10 meters per second squared that way. Okay. So that's what we're going to use. So let me just get into that with a couple of example problems, and hopefully you'll sort of see how it works. Okay, so the first one is going to look sort of like the problem we just did. So we have a pulley hanging from the ceiling. And a 10 kilogram box over here. And then over here, let's say we have a 5 kilogram box. Okay, so we're not applying a known force anymore. We just have another mass at the other end. Okay, so first of all, intuitively, what's going to happen here? Yeah, the 10's going to go down, and it's not just going to go down, it's going to accelerate down. Okay, so it could even be the case that you could start this system. So say that you started this by pulling for a couple of seconds really hard on the 5 kilogram. Okay? And then at the instant that you're analyzing with Newton's second law, that's the instant you let go. Okay? So this is what's going on at that instant, but this is moving up with some velocity and this is moving down with the same velocity. Can you imagine that? No? Just give it up. Well, I mean, you could just, if you pull really hard, this will, for a little while, keep moving down. So imagine that it's doing that. Well, that means that this would be moving up. We know that the acceleration that we expect is the 10 kilogram box moving down. Okay. So what happens if you have an upward velocity and a downward acceleration? Think about like lab, what is that? What's a way to describe a velocity one direction and acceleration the opposite direction? It's slowing down, yeah. And so that's what would happen. If you pulled really hard on this to start with, it would start out going down, this would start out going up, but it would slow down until it came to rest, and then it would start speeding up the other direction. So all we're going to calculate is the acceleration, because that's all that comes into Newton's second law, and this acceleration would apply no matter what the starting velocities are. It doesn't matter, it's all the time. So even the acceleration, while they're still moving in the funny direction, is going to be the same as the acceleration once the 10 starts moving down. Okay, it's sort of a hard thing to get used to, but you can think of it sort of like free fall, projectile motion. If you throw something up into the air, while it's going up, gravity's making it accelerate down. When it's stopped for an instant, gravity's still making it accelerate down. And then when it starts coming down, gravity's still making it accelerate down. And that's what's happening here. Yeah, they are. So we only have 3 inches to play with. So we have to do this calculation really fast. Okay, so let's first ask the question. So what's the acceleration of the 10 kilogram box? And second, what's the tension in the cable? All right, so the first thing I'm going to do is isolate the 10 kilogram box. There's a weight force down of 98.1 newtons. And there's a cable force up. I'll call that T. We don't know what that is. We're trying to calculate that. And Newton's second law says 0, negative 98.1 plus 0T is equal to the mass, 10 kilograms, times the acceleration. And now we have to think, just like we did with those rolling problems, what kinds of accelerations are going to happen? Do we expect any motion along the x-axis? No, so it's only y. And we said that, you know, our intuitive understanding, because this is a pretty simple system, is that the 10 kilogram box is going to accelerate down. But we don't even need to do that. We just need to identify which axis it's going to move along. Okay, so I'm actually going to call the acceleration 0 positive a. Okay, it doesn't. You don't have to get the sign right. The sign will work out in the math. Okay. So I'll call this 0a. This here is the acceleration vector of the 10 kilogram mass. If we get a positive value for the variable a, it's going to be accelerating up. If we get a negative value for the variable a, it's going to be accelerating down. The x equation doesn't help, so I'm going to look at the y equation. And that says negative 98.1 plus t is equal to 10a. And now we have a problem that we haven't encountered before. What's the problem? Yeah, one equation, two variables. So what I'm going to do, I'm going to write, you don't have to do this, but I'm just going to put it in a form where it'll be easier to use later. So t is equal to 10a plus 98.1. And I'm just going to set this aside. I'll call this equation star. Yes. And now we're going to go on and isolate the 5 kilogram mass. Eventually, we're going to have a system of two equations that we can use to solve for these two variables. So we'll come back to that. But we can't go any farther with it right now. Okay, so now we'll do a free body diagram of the 5 kilogram. So the weight is 5 times 9.81, so 49.05. And the cable force, what way is that going to pull? Up. It's always away from the chosen body, so that's also up. And what are we going to call that one? T, because it has to have the same value as the other one. It's the same cable going through pulleys. So now Newton's second law says 0, negative 49.05 plus 0t is equal to the mass of the chosen object. And now we have to assign this an acceleration. And this is where we have to be careful about the relationship between the motion of the two objects. Okay. Now, this one also is only going to move up and down. Okay. But we've already chosen a default direction for this system. When we said that the acceleration of the 10 kilogram box was 0a, we said that our default direction for the 10 was going to be a up. Okay. So it's like, imagine moving this one an inch up. Where's this one going to go? That's going to go an inch down. So if this one has an acceleration of 0 positive a, this has to be an acceleration of 0, negative a. So this is 0, negative a. This is the acceleration of the 5 kilogram. And that negative comes from the relationship between those motions. What if just I happen to think like I'm used to reading left to right, and so I isolated the 5 kilogram box first. And then I did Newton's second law and called the acceleration of the 5 kilogram box 0a. And then I had to call this one acceleration 0, negative a. Would that be a problem, do you think? It would not be a problem. Our variable a would just come out being the opposite thing. And when you plugged it back into the acceleration vectors, you'd get the exact same answer no matter how you did it. Okay? So those signs are going to work themselves out. All you have to keep track of is the relative, the relationship between the motions of the two objects. Okay. All right, so again, the x equation doesn't do us any good. The y equation says negative 49.05 plus t is equal to negative 5a. Can't solve this one by itself because there's two variables, but they're the same two variables in our equation star. So now that equation star and that equation double star is a system of two equations for two variables. And that means you can solve it by substitution or however you want to do it. Okay, so I'm going to, I already put equation star into this nice format, make it easy to substitute. So I'm just going to substitute this equation star into equation 2 star. What was it? T is 10a plus 98.1. So now equation 2 star says negative 49.05 plus, I forgot again, 10a plus 98.1, I think, is equal to negative 5a. And that says that 15a is equal to negative 49.05. And that says that a is negative, is that 3.27 meters per second squared. And now if what we really want is the acceleration vector of the 10, how do we use this variable to get the acceleration vector of the 10? Yep, plug it back into this vector here. So the acceleration vector of the 10 kilogram is 0, negative 3.27. Or in other words, that's in the negative y direction. So you could also think of that as downward with a magnitude of 3.27. And now let's say we want to figure out, well, part B was to figure out the tension in the cable. So you can just find any relationship between T and A. As long as your math is right, any equation you have listed up above is correct. You know, it's true. It's a true statement. So they all have to work. I guess maybe this is the easiest one to, you know, because it's already solved for T. So T is equal to 10 times negative 3.27 plus 98.1. 10 times negative 3.27 plus 98.1. And that is 66.4. Oh! Okay, so the tension in the cable is 65.4. Okay, I'm over it now. It's just so frustrating. Okay, so one thing to notice here is that's sort of a subtle thing. Tension does not have a direction. That's just the magnitude of the force that cable's applying everywhere. So that's just a number. But then if you ask what's the force vector that the cable applies to something, then that would be a vector. That does have a direction. But tension is just a number, a positive number always. Yep, that's Newton's. And by the way, I always try to be pretty good about if the capital N is for newtons, I just write it like that. And if it's a normal force, I write it with like fancy shoes and hat, so you can tell the difference. Well, notice that the tension in that cable is not the same as the weight of either one of those two masses. You might think it would be, but it's not. It was when that 10 kilogram mass was at rest, to hold it at rest, you did have to pull exactly with its weight. But if you have accelerations, that doesn't work anymore. You can't assume that's true. Yes? Yeah, well, same variable A and plug it into this acceleration vector. That's right. So there are a lot of times when the answer that you want is going to be, so you're going to solve for some variable. It can be a force variable or an acceleration variable. And then you're going to plug it back into a force or an acceleration the way you wrote it in Newton's second law. Equal and opposite. That's right. Yep. Yeah, so the force that cable applies to the 10 kilogram mass is up at 65.4, and the tension force, the force that the cable applies to the 5 kilogram is also 65.4 up. Yes? No, because we notice our acceleration vector expressions, we already dealt with the direction. So you take the negative 3.27, plug it in there, and you get 0, positive 3.27. There is a way to do that, but I would not recommend doing that. I would recommend just, even though it's arbitrary, you're going to say one of those is moving in this direction, and so it's, you know, 0A or A0. And the other one, then you look at what happens if you move this one an inch in the positive X or positive Y direction. What happens to the other one? Any other questions? Let's do another one. So again, let's figure out, this time let's figure out the acceleration in the 1 kilogram. And let's figure out the cable tension. Okay, so it doesn't matter which one of these we decide to be positive. You can do it in either order. I guess I'm going to do this one first. So let's think about the motion of this. What kind of motion is allowed? Is it going to move along the x-axis or the y-axis? X-axis. This one, yeah. And so if we move this one an inch in the positive x direction, where does this one go? An inch in the positive y direction. Okay. So I'm going to isolate this first and call its acceleration a0. And then when I isolate this one, what am I going to call its acceleration? 0a. Okay. Any questions about that?
Can you repeat what you said?
Yeah. So I'm going to isolate this one first. And I'm going to say its acceleration is a0. I'm just going to say positive x direction. Obviously, looking at it, you can tell that variable a is going to come out negative. But I don't care. It's no harder to solve for a negative number. So that one's going to be a0. So what's this one going to be? If you move this an inch in the positive x, this one goes an inch in the positive y. So this is going to be 0a. The acceleration of the 1. Okay, so first free body diagram of the 5. There's a weight force of 49.05. There's a pushing contact from the ground. I'll call that N. And then the cable's pulling on it away from the chosen body. So T is like that. And so Newton's second law says T is in the negative x direction. So that's negative T0. The weight is 0, negative 49.05. The normal force is in the positive y direction, so that's 0n. There are no other places where the surroundings touch the boundary, so that's all of F net. And that's equal to the mass of 5 times A0. And so this here is the acceleration of the 5. We just don't know what the variable A is yet. Once we know it, we can just plug it in there. No, I mean, that's just the one I happen. I know I have to isolate both of them, so I just picked one at random. Right. Okay, so this time you actually could solve for that normal force with the y equation, but we don't happen to care about the normal force. All we want is that A. So I'm gonna just equation and just skip the y equation. So this has negative P plus 0 is equal to 5a. And I can rewrite that as t is equal to negative 5a. And you don't have to do that, but I just know that's going to make it easier to plug it in later. Because that's an equation we're going to have to come back to later. It's one equation for two variables, so we can't do anything else with it now. But when we get the second equation, we can use it to solve. And then the free body diagram of the one. There's a weight force of 1 kilogram times 9.81. So that's 9.81 newtons. And then the cable's pulling up on it with a magnitude T. And then Newton's second law says 0, negative 9.81 plus 0T is equal to the mass, 1, times the acceleration. And this is where we have to use the relationship between the motion of those two things. We said that that first one is moving in the positive x. So what are we going to say the second one? 0a. So this is our vector a1. We just need to solve for a first. And this comes from the relationship between the motions of the two objects. In the first Newton's second law, the x equation was the useful one. In this one, the y equation is the useful one. So negative 9.81 plus t is equal to a. And now we can use equation star and double star as a system to solve for a and t. Okay, so I'll plug in negative 5a for t. That's what we had from equation star. So this one becomes negative 9.81 plus negative 5a is equal to a. And so we get negative 9.81 is equal to positive 6a. And so what do you get for a? Negative 1.635a is equal to meters per second squared. And so that means that the acceleration of the 1 kilogram mass, we had it right here in Newton's second law, there. So just plug in your value of a, and it's equal to 0, negative 1.635. Yes. Yep. Okay. But yes, you can totally do that. And then what did you get for t? You don't know. Yeah. So, well, I guess it's negative 5 times this, or 8.175. 8.175. Oh yeah, newtons. No, I mean, it matters. You have to pick the right one, but it totally switched around directions like that. Yeah, that's right. Yes, exactly. If you ever get a value of t that's negative, something went in a way that you didn't plan on. It could be, sometimes it's sort of harmless. You go back and you find the error and your answer didn't change, but you should always go back and find where the mistake is because sometimes it screws it's something that messed up everything. So if you, um, so if you get a, like t is equal to negative 50, what you should not do is just be like, just call it positive 50. Yeah, because often that's the only indicator you have that something went wrong. It's trying to help you, you know, to let it help you. Right. Well, the reason it always works out positive is because we always know what direction the cable force should pull, and we always specify that it's in that direction. And so if we always choose right, then it always comes out positive. Any other questions? Okay. Well, um, if all pulleys do is change the direction of a pulling force, or let's say the direction of the forces applied by a cable, then what's pulley advantage? Change the direction. Okay. Okay, well, if you rig up pulleys in a very specific configuration, so it's not really a property of the pulley itself, it's a way you can use a bunch of pulleys. Then you can lift heavy things by applying a force smaller than its weight. Let's say you can lift a heavy thing by applying a force smaller than its weight. And you wouldn't think off the top of your head that that would be possible. We saw for the 10 kilogram mass, to hold it still, you had to apply a force on the other end of the cable of its weight. To make it accelerate up, you had to apply a force bigger than its weight. So there shouldn't be any way to lift a force to lift that object by applying a force smaller than its weight, you would think. So let me show you an example of a configuration that can do that. Mhm. This, yeah. Uh, yeah. Well, if she would have rigged up pulleys like this, she could have made it easier on herself. Okay, so here's the ceiling, and here's a pulley, and here is another pulley that's not connected to the ceiling. And the mass that we're trying to lift is hanging from that one. So let's say this is 10 kilograms. And now a cable goes through this pulley up to the ceiling. And from this pulley up over the second pulley. And now let's figure out what the cable force T is to keep that at rest. Yeah. Yeah, I think that's a good way to think about it. Yep. So what's the cable force T that's required to hold, let's just say to hold it at rest, because we already did that problem. To hold the mass at rest. And what do we know from that previous example? We know that anything less than 98.1 newtons would be amazing. Okay? Get ready to be amazed. No. And actually, if you remind me sometime in lab, we have pulleys and everything. We could show you how to do this. It would take 5 minutes, and you can feel it very clearly. You're applying a lot less force than the weight of the thing to lift it. Question? Okay. All right. So what are we going to isolate? So I'm going to isolate mass and the whole pulley system attached to it. So I'm going to do a free body diagram of the mass and the hanging pulley. Okay, so an outline of that system looks something like this. Okay. And just to make it a little simpler to see, I'm going to also include, correct this. I'm going to include the bit of cable that goes underneath that pulley. So under that hanging pulley. Okay, so now there's a little bit inside of this outline, a little bit of cable. And then at some point we have to make the distinction between where the cable that we're including ends and the cable that's in the surrounding starts. So that's what those little bad ears are, like stumps of the cable there coming out from under the pulley. Everything there is perfectly legal. Okay, so what forces are acting? There's a weight force of 98.1. And then the cable is acting parallel. So the cable force is parallel to the cable away from the chosen body. So there and there. And it's the same cable, so we'll call them both T. Now, Newton's second law says 0, negative 98.1 plus 0, positive T plus 0, positive T is equal to the mass of the system, 10, times the acceleration, and we're assuming it's at rest, so that's 0. And so the y equation says negative 98.1 plus t is equal to 0. Or in other words, T is equal to 49.05 newtons. So you can hold that weight up by applying a force half as big as the weight of the object. Pretty cool. They use that in like anything like shipping yards and train yards and anywhere that big things have to be lifted. You can do it with more than one hanging pulley, and each time you're reducing the amount of weight you have to, the amount of force you have to apply. Yep. It's always half if you just have one hanging pulley like this. Well, and it depends on the angle. So it's half. It turns out that if this isn't right underneath, like if these ropes aren't vertical, then that force required can go up. And in fact, as those get closer and closer to horizontal, this gets close. It doesn't approach. You think, okay, maybe it approaches 98.1, the force you have to apply. It doesn't. It approaches infinity. So if you're trying to save space by spreading these way out, you're actually making it harder to lift. And
so is there a way to get less weight on the downward force and more weight on the static? With the attached ceiling?
I don't think so. No. Yes. You have all those little bits of rope in between. I guess I would say, yeah, it's probably possible in theory. Although the more pulleys you include, the more friction and pulley weight and stuff you're adding that this way of calculating it doesn't see. So you have sort of hidden things that are fighting against you. But yeah, I would imagine that is possible. Yeah. So then I guess the reason they do this is because not only can you hang it there, which the ceiling can do, you're right about that, but you can lift it. But the interesting thing about lifting it is, so here's the trade-off, because you can't ever get anything for free. You can't get energy without putting energy into it. And so the way conservation of energy gets you is, okay, it's less force here to lift a bigger weight force here, but if you want to lift this 1 inch, you have to pull this down 2 inches. And the more pulleys you add, you're doing this just to get a tiny little motion. You can make the force go down, but then the trade-off is you have to pull a lot more rope to make it move. Okay, that's it. Have a good weekend.